So let's take a look at geometric series. So what we have is a geometric sequence, a sub n, and what exactly does that mean? Well, it means that a sub n is equal to a times r to the I minus 1. Oh, I'm sorry, n minus 1. Okay, so that's what that's the definition of arithmetic sequence. And now what we want to do is find the sum from I equals m to n of a sub I, and we want to know what that's going to be equal to. Okay, so so let's go ahead and try it, and let's kind of do it with brute force. Okay, so we have the sum from I equals m to n of a sub I, and just based on the definitions of geometric series, then what we'll have is that this is equal to a sub m plus a sub m plus 1 plus a sub m plus 2 plus dot 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 up till we get to a sub n. Okay, so that's pretty easy. Okay, and what I'm going to do is kind of think of r times this sum. And the reason that I'm doing that is because I can write down r of a sub m here, and r of a sub m plus 1 here, and r of a sub n minus 1, and then r of a sub n. Okay, and I'm actually going to subtract these two, so let me just put minus signs everywhere. Okay, and the reason I'm doing that is so that I can now kind of add these two rows together. So the sum from I equals m to n of a sub I minus r times the sum from I equals m to n of a sub I is going to be equal to, well, let's see, we have a sub m plus 1, a sub m plus 2, plus a sub m minus r times a sub m minus r times a sub m plus 1, r times a sub n minus 1, and then r times a sub n. Okay, and so now we can use the basic definition of what it means to be an arithmetic sequence. So this is a times r to the m minus 1, a times r to the m, plus a times r to the m plus 1, a times r to the n minus 1. Okay, and what I'm subtracting is r times a to the r times a times r to the m minus 1 minus r times a times r to the m, and dot dot dot, and this is a times r to the r times a times r to the n minus 2, and this is r times a times r to the n minus 1. Okay, so when I subtract these, I end up with a times r to the m minus 1. Okay, this here, well, these two are the same, right? Because this is a r to the m, this is r times a times r to the m minus 1, so these just cancel, that's just 0. These two, same story, right? That's just 0. These two, again, I have r times r to the n minus 2, that's r times to the n minus 1, yeah, that's the same. And so I'm simply left with minus a times r to the n, right? And I'm combining this r and the r to the n minus 1. So really all I have is a times r to the n minus 1 minus a times r to the n. Okay, and I can actually simplify that even more, because this first term you'll recognize is just a sub m, and this term, well, that's actually a sub n plus 1. Okay, so so there's our answer. Okay, now to finish this, right, all we need is kind of one more summary here. So we have the sum from I equals m to n of a sub I minus r times the sum from I equals m to n of a sub I. That ended up being equal to a sub m minus a sub n plus 1. Okay, so I'll factor the sum here. 1 minus r times the sum from I equals m to n of a sub I is equal to a sub m minus a sub n plus 1. And finally, the sum from I equals m to n of a sub I is a sub m minus a sub n plus 1 divided by 1 minus r. Okay, so that's the result that I want. So QED. Okay, now this, as before, is actually a convincing argument, right? The only thing that's suspicious, I guess, is the dots. Okay, and again, if those dots were like an infinite sum, then this wouldn't work at all. Okay, so we want to be more precise, and the way we can do that is by simply trying to do this proof with induction. Okay, it's actually a lot easier to do with induction, but let's go ahead and make that argument. So the theorem that we have is that let's say that a sub I or a sub n is typical, is a geometric sequence. Okay, then the sum from I equals m to n of a sub I is actually equal to a sub m minus a sub n plus 1 divided by 1 minus r. Okay, so this is what we want to prove, and our proof will be by induction. So the base case is when m is actually equal to n. And let's see what happens in this case. What we have is the sum from I equals m to n of a sub I. Well, that's actually just the same as the sum from I equals m to m of a sub I, because m is equal to n, and that's actually just a sub m, right? Period. Okay, and what happens is that it's of course equals to a sub m times 1 minus r divided by 1 minus r, which is a sub m minus r times a sub m divided by 1 minus r, and that is a sub m minus a sub m plus 1 divided by 1 minus r. And this here is what we want, so yes, it works in the basis case. So let's consider the induction step. So the induction step, this is the case where m is actually less than n. Okay, so let's see what we can do. The sum from I equals m to n of a sub I, we'll split that up into two. The sum from I equals m to n minus 1 of a sub I plus a sub n. Okay, and now we can use the induction hypothesis here. So this is where we use the induction hypothesis, because this sum we'll know is actually a sub m, okay, minus a sub n minus 1 plus 1, which is just a sub n, divided by 1 minus r, and we have to add to that a sub n. So this is going to be equal to a sub m minus a sub n divided by 1 minus r, and I'll bring this up here, times a sub m 1 minus r. Okay, well, actually at this point we're pretty much done, because this is equal to a sub m minus a sub n plus a sub n minus r times a sub m. These terms will cancel, and that's equal to a sub m minus r times a sub n. That's a sub m plus 1 divided by 1 minus r. Okay, so yes, it is true. What we have is the completed proof. So that's how we can do geometric sequences using induction. And I think in this case you'll probably agree that the induction proof is easier in many ways than the informal dot proof. If for no other reason, then it's easier to keep the algebra straight.